Hey friends, MoNaCo here with our third lecture notes on heating and cooling curves. We're covering that today. We're going to describe what's happening in terms of energy and phase changes, potential and kinetic energy, during those phase changes of solids to liquids to gases, and how these look on paper graphs. You might be asking yourself, well, isn't heating water pretty simple? Why would we have to bother looking at this stuff? Well, it is very simple, but we as chemists love to make simple things very complex as we describe them. So we need to get familiar with how kinetic and potential energy change along with our solid, liquid, and gas phase changes, along with the terminology that we use. So let's get into it. Talk about a heating curve first. A heating curve is temperature versus time. Temperature's on the y-axis, time's on the x, as we're heating a substance. 99% of the time, we're talking about water. That's what we're heating. Now, when we talk about this chart, we got to make some annotations to it. You might want a colored pencil here because it's going to help us out quite a bit. Let's put our annotations in for our phases. During the solid phase, we got an S. During the liquid phase, we got an L. And during the gas phase, we got a little lowercase g. Now, let's talk about this flat line, transitions, the phase changes. From a solid to liquid, so we got an S turning into an L. We call that melting. We also call that fusion sometimes. That's the new term that you need to get familiar with. The other phase change on this chart is the liquid to the gas, L to G. We call that vaporization. Oof, big long word. Yikes. Now, I want you to get out your colored pencil or a marker or highlighter, two different colors, and highlight two different sections of the graph. Kinetic energy is changing in the areas where we have our temperature changing. So in the sloped portion of the graphs, kinetic energy is changing. Highlight those one color to help burn this into your brain. Kinetic energy is changing there. Now, during the other portion of the graphs, potential energy is changing, while kinetic energy is constant. You are going to highlight the flat portions or the phase changes, that color. Okay, those are the two things that are happening. How energy changes along with a phase change. So let's get these down in some notes here. The interval sections of the graph, A, B, C, D, and E. The phases, the numbers and the name of these phases on that first section of the graph. The first section, one of the animation's not working. But the first section of the graph is 1, a solid. Second section B, 2 phases, solids and liquid. Section C, 1's a liquid, 2, etc. So this is according to the annotations we just made, we're just charting them. The change in temperature in section A is increasing because it's a sloped line. In section B and D, there is no change in temperature because it is a flat line. The change in kinetic energy, again, that's kind of related directly. In your mind, you can almost think delta T equals delta KE. You can see that the kinetic energy changes when the temperature changes because they're kind of a synonymous definition. Now, potential energy, that's the new thing that we started talking about today, and it's inversely related to kinetic energy. So whenever kinetic energy increases, potential energy doesn't. They're opposites, okay? Again, they're related to the flat portions of the graph versus the angled portions of our graph. And that was a heating curve. Now, you might see a cooling curve as well. It's the same idea. Stuff is being cooled down at a constant rate. Now, this one doesn't have the annotations in it, but when we do a cooling curve, we always start at the highest phase gas, move to liquid, and then finally finish with a solid. These transitions, in here we have gas becoming a liquid. We call that condensation. Big word, condensation, squeeze it in there. When we have a liquid turning into a solid, we have freezing, synonymous with fusion again. And then, of course, obviously a solid at or below the freezing point. So that is just a flipped version of our heating curve. Cooling curves, we go through the same types of phase labeling. Okay. Now, in this section, you'll notice that we called this a section A to B. It's kind of like line segments in mathematics. Sometimes the sections will be labeled with a single letter. Other times there'll be line sections like that in mathematics. So be able to do that by looking at the graph in both ways. Temperatures decreasing in the first section of the graph. And potential energy stops decreasing when you get to the flat portions of the graph. Again, because temperature and kinetic energy are pretty much synonymous with each other. There's a direct relationship. As temperature decreases, kinetic energy decreases. And again, these are the sloped portions of the graph, and the potential energies are the flat portions of the graph, denoting phase changes. During a phase change, the potential energy in a cooling curve decreases. But when the temperature is changing, potential energy doesn't. Potential energy and kinetic energy, inverses of each other. This is where we label our all-important names of our phase changes. And we relate energy increasing, and put that a little bit in red there, and decreasing to those said phase changes. Okay, so let's label them up. When we have a solid going directly into a gas, we call that sublimation. When we have a gas turning directly into a solid, we call that deposition. It's the opposite of sublimation. When we have a solid turning into a liquid, we call that melting or fusion. And we have a liquid turning back into a solid, we call that freezing / solidification. I like freezing better. Fusion is also used, but solidification is kind of like this overarching idea of when you turn a liquid into a solid. You may see it in the Regents exam or our quizzes and tests in that manner. Now, last thing we're going to cover is a gas to a liquid. When you turn from a liquid into a gas, we call that vaporization. Good luck fitting that on the line. And when we turn from a gas into a liquid, we call that condensation. Again, good luck fitting this on the line. Condensation. So those are the all-important terminologies related to energy and phase change. So again, look at the big picture. When you go up from one phase to the next, or solid to liquid to gas, you're increasing your energy. And when you come down from gas to liquid to solid, you are decreasing your energy. So let's see what that all means. Endothermic and exothermic are new terms for increasing and decreasing energy. Pardon me. An endothermic system absorbs or takes in the heat. An exothermic system gives off the heat. So you would think giving off the heat is hot and absorbing the heat is cold. Okay? That's how your body would think and feel endothermic and exothermic changes. The graph below helps us answer some simple questions. At what temperature will this substance boil? Whenever I see one of these graphs, the first thing I always do is label them up. Solid, liquid, gas. Why? Because those are the three slants, and I know one for each phase. Now, what temperature will this substance boil? I think to myself, boiling, well, that's vaporization. So we call this right here the liquid to gas change, boiling / vaporization. And so we look over to see the temperature, we see it's about 90 degrees. So that's how we are interpreting these visual charts. At what temperature will the substance become a liquid? Become a liquid. So becoming a liquid means it's turning from a solid to a liquid at this time and that temperature, 60 degrees Celsius. So I'm just interpreting the melting and freezing points and boiling and vaporization points from this chart. Between 55 and 90, the kinetic energy of the substance is. So here we have to look at our temperatures. So between 55, which is right here, and 90, which is right here, what's happening to our kinetic energy? So you got to know the definition of kinetic energy and how it's related to temperature. And since you can see that the temperature here during that time is increasing, you can say that kinetic energy is increasing as well. Because Ke and temperature are pretty much synonyms. At 90 degrees, the potential energy of the substance is, well, 90 degrees, the potential energy of the substance, we can see is this point, 90 degrees, potential energy is constant. It is flatline. There's no change in the kinetic energy, so that means the potential energy is increasing because it's going through the phase change of liquid to gas. Whew. A lot of stuff dealing with heating and cooling curves. Hint, hint, very important. Getting almost done here. We got some definitions of exothermic and endothermic. So definition-wise, exothermic is a system that releases or gives off heat energy. You might think that it feels hot. Examples, well, freezing and condensation. Those don't feel hot, but they are releasing heat. When you turn from freezing, you're turning from a liquid to a solid. In condensation, you're going from a gas to a liquid. So a liquid to a solid, you're releasing the heat that you had. From condensation, you're going from a gas to a liquid. You're releasing heat. Non-examples for exothermic systems are endothermic systems, the opposite. Now we've covered endothermic definition. This is a system that absorbs or gains heat energy. To you, this would feel cold because the system is gaining heat energy. It's taking it away from you. You would feel the absence of heat and your brain thinks cold. Examples are melting and boiling. Melting being a solid turning into a liquid. This takes heat. If I want to turn ice into liquid, I have to put heat into it, which means it absorbs the heat. Boiling, liquid to gas. Again, if you want to turn liquid into gas, it has to absorb heat in order to do that. Non-examples would be exothermic reactions. Now your head might be spinning around right now going, oh, so many terms, so many terminology, so much heating curves and cooling curves, and it might be the case. This was a rather intensive video. You may have to watch it a couple times, but now you should be able to understand those basic heating cooling curves and what portions of which curve is related to which terminology, like kinetic energy, potential energy, changes in state. So we have a practice pack page for you, a Castle online learning quiz for you, entitled Energy and Phase Changes. So thanks for watching.